So if there's anything clear from the previous videos is that everything is about variables, about the things that we measure. And we saw that we can distinguish between independent and dependent variables, but we normally also distinguish between quantitative variables and qualitative variables. So a quantitative variable is one that takes numerical values. So think about the age of a person, a response time, a test score, things like that. A qualitative variable is one that does not have numerical values, or if they do, they don't make any sense. They are completely arbitrary. Think, for example, the sex of a person, a programming language, a company, a country, things like that. Sometimes they can be coded as numeric. So we could say, I don't know, the Netherlands is 1, Italy is 2, France is 3, etc., but those numbers are completely arbitrary. They're meaningless. The thing is that these variables can be aggregated. Can be composed. We could play with them in different ways. We will see some later in these videos. So we could, for example, think about a company size variable that could be composed of multiple variables such as the number of employees, the year of foundation, the number of departments, the age of the CEO, the sector the company belongs to, revenue, number of clients, number of providers, etc. Those are all certain variables that are correlated with this general notion of how big the company is. And we could just aggregate them in a certain way, for example, to have this one measurement of company size. There's two characteristics that we have to always keep in mind when thinking about variables. One is that they should be exhaustive. So that means the levels of the variable, the possible values they could have, has to be exhaustive in our study, and they have to be mutually exclusive. So by exhaustive, we mean that we need to include all the possible values that those variables could have. Now, there are situations in which there are too many. And in those cases, we could, for instance, ask people option 1, 2, and 3, or something else. If we are dealing with numerical variables, maybe we could ask in a certain way that we are sampling some of the values. So if we're interested in something between 0 and 100, maybe we could let people tell us 0, 10, 20, 30, etc., instead of a fixed number. Or if we want to study specific numerical quantities, such as the pressure of the coffee machine, we could just sample different points in the pressure scale to make observations in those points. When doing this, we have to be careful about two things. One is we have to be careful about what happens in the bounds of the scale, because usually there's some funny behavior around the boundaries of the scales, and linearity assumptions. Maybe we assume that the relationship between this variable and the response variable is kind of linear, and so we just sample these values uniformly across the scale, when maybe we shouldn't. We should pay more attention to lower values or higher values, because that's where most of the effect is happening. Something that is better is to sample at different quantiles, so at points that are dividing the scale in equally sized groups of data. Sometimes what we can do is just group levels altogether. If, especially after, for example, running a survey, we see that we have very few options, 1 and 2, few observations in which people told us 1 and 2, then maybe for analysis, it's better if we just say 1 and 2, one of the two. We need to be careful with interpretations here, because what we are analyzing is not really what we were asking for. But sure, this happens all the time. Typical case is we try to represent all groups of age in population, but then we have a lot of people in their 15s and 20s, and we don't have a lot in their 40s, 50s, 60s. Then we could just group together people of 40s, 50s, and 60s, so that we have a good representation of that group, even if it doesn't have the resolution we would like to. The other property about these variables is that their levels should be mutually exclusive, meaning only one level is possible for any given observation. This is something very funny that happened in the US all the time when I was there. If you have to fill in a form, you have to say whether you are Hispanic or Caucasian, among other options. Now, I'm from Spain. That means I'm both Hispanic according to their definition and Caucasian, but I can only choose one option. In these cases, you could say just check all that apply. And then in the what's going to happen in the analysis is that instead of having one categorical variable with all the possible answers, we have one binary categorical variable for each of the levels. So we will have one for Hispanic, yes or no, one for Caucasian, yes or no, one for African American, yes or no, etc., etc. And it's very important to be careful with the actual words we use for these levels, because there are cases in which just a poor selection of the wording or the actual levels may hide effects or introduce bias. So for instance, think about the case in which we want to study the relationship between people being employed or unemployed and something else. If we just ask whether people are employed or unemployed, then we are not making any difference between people who are moonlighting or not. So people that have multiple jobs. And that could be a crucial difference in the relationship we're trying to establish. It's not only whether people are employed or not, but it's really about how many jobs they have. Or if we want to rate the damage of a car wreck and we show people videos of the different accidents, then depending on how we ask, we might get different results. So it's not the same to ask, rate the damage from the accident between low and high or between low and brutal. People are very rarely going to go all the way up to the brutal point because it has certain connotations as opposed to low versus high. Or we could say in a flight, this actually happened to me not long ago. So they were asking passengers to rate their experience in today's flight. And the options we had were poor, fair, good, very good, or excellent. And if you see, well, most of the options are actually positive. Good, very good, or excellent. There's only one option that is poor. So if we were to assign numbers to these levels, say poor is 1, fair is 2, etc., then sure, we're going to have a high number because most of the answers are positive and they have the high numbers. So in here, we're kind of already biasing the possible answers that the passengers can give us. We should ask very poor, very good, poor, good, etc. But there's a certain distinction that is even more fundamental than on this, and that is the level of measurement. And the thing is that the variables, just by their own nature, by what they represent and how we measure them, they are on a different level. And there are several theories of the levels of measurement. The one more accepted one is the one by Stevens. And the categorization is in 4 types: nominal, ordinal, interval, or ratio. Nominal variables are those that we typically call categorical. So those are qualitative classifications. So for example, the sex of a person, men, women, etc., nationality, Spanish, Dutch, German, French, etc., programming language, C, Java, PHP, R, Python. Those are just categories. There's no relationship between them other than being equal or being different. Then we have variables who are ordinal. And those are the ones in which there is a certain order. So one level of the variable comes before the other one. It's smaller than or larger than, but we don't have a sense of magnitude. We don't have a sense of how far before or how far after. So think, for example, of agreements. Do you agree with this statement? Yes or no? Very much agree, very much disagree. Those are things that go before or after some others. Difficulty, none, some, or much. We know that none comes before some, comes before much, etc. But there's no notion of how far before, how far after. Then we have interval variables in which there are magnitudes, which, by the way, also happen to be equally spaced, but we don't have ratios. We don't have a zero. So things like the temperature, 5 degrees and then 7 degrees. We know that 7 degrees is 2 degrees more than 5. 7 not only comes after 5, but it's 2 units apart from 5. Dates. So we could have September 5th and September 10th. And we know there's a difference of 5 days between the two. And finally, the 4th level of measurement is ratio variables. And the difference is essentially that we do have a zero value, something that has a specific meaning. And the point in this case is that we can do ratios between two quantities. So think about temperature again. You notice that it's both interval or ratio. I'm going to tell you later why. But you can think about the length. So we know that 6 centimeters is twice as much as 3 centimeters. And the reason why we can make that statement is because there is the value of 0, which has a very clear meaning. 0 centimeters means no length. And therefore, we could make a ratio between 6 and 3, for example. Duration in seconds. 2 minutes is twice as much as 1 minute. We can make that. It's not only 1 minute apart, it's also twice as much. Mass in kilograms, things like that. And this is important because the kind of statistical operations we can perform on the variables depend on their type, depend on the level of measurement. So here with this big table, we are going to try and summarize everything. So we have here in the columns the nominal, ordinal, interval, and ratio variables. And then we have different kinds of operations. So for example, all variables, even if they are nominal, we could put them together or not. It makes sense to say these belong to one group, these belong to other group based on whether they are equal or not. So it does make sense to do all this. However, if we want to sort them and say one value comes before or after another one, we cannot do it in a nominal variable. We need it to be at least ordinal. So it doesn't make sense to say Python comes after PhD. Well, with respect to what? They're just two different things. If we want to compare to a certain reference, the variable has to be at least interval. So we cannot do it with ordinal variables. So we cannot just say 6 is 4 units apart from 2. We need to be able to assign these numbers, and they have to be at least on an interval scale. And then ratios. We cannot compute ratios unless we have a ratio variable in which we do have a sensible value of 0. And this is very much related to arithmetics. So all variables, we could in principle say whether two values are equal or different. If we want to be able to say something comes before or after, we need it to be at least ordinal. If we want to be able to add or subtract, we need it to be at least interval. And if we want to be able to multiply and divide different values of the variable, we need it to be at least ratio. What kind of statistics can we compute in terms of central tendency? Well, as we saw in the videos on exploited data analysis, when we have a categorical variable, a nominal variable, we could just compute the mode. It's the only thing that makes sense with this kind of data. If we have ordinal, interval, or ratio, we could compute the median. So what is the point that divides the whole distribution in the top 50% and the bottom 50%? We could do this. But if we want to compute the arithmetic mean, the typical average, then we need the variables to be at least interval or ratio. It doesn't make sense to compute averages or the means with ordinal variables. And then we have measures of dispersion. What kind of things can we compute? If we have nominal variables, we could always do at least entropy and variation ratio. We again saw that in the lecture on exploited data analysis. If we want to be able to compute ranges, interquartile ranges, things like that, we need it to be at least ordinal. If we want to compute deviations, we need it to be at least interval. And things like the coefficient of variation, which, if you remember, was dividing the standard deviation by the mean, we need the variable to be at least ratio. So you see, it's not just being picky with whether our variables are nominal, ordinal, interval, or ratio. Is that depending on their nature, this is very much their nature and how we measure them, we are going to be allowed to do one thing or another. Let me show you a couple of examples. So here we are going to talk about ordinal variables versus interval variables. So let's assume a variable is defined as ordinal, and we just gather some data. Let's say we are measuring somehow the difficulty of something. And the possible values are none, which comes before little, which comes before some, and which comes before much. Let's say the data we gather is some, much, little, none, some, none, much, some. Now, the observations may be sorted, of course, depending on this scale we defined here. So we could compute something like the median. If we get the data sorted, it looks like this. The median is the midpoint, which happens to be sum over here. So the median in this data is sum. Now the median is the same even if we assigned numerical scores, which would be arbitrary anyway. That's why the median still works. So let's say we assign these arbitrary numbers in which 0 corresponds to none, little corresponds to 1, sum is 2, and much is 3. Then the data will be transformed into something like this. And still in this case, because we're just sorting and this is okay with ordinal variables, we could just compute the median. It's a number 2, which again corresponds to sum. So the result will be the same regardless of what scale we use. However, the mean is not permitted in this case because it's sensitive to this numerical assignment. So let's say that instead of assigning 0, 1 to 3, we assign 0, 1 to 5. So here's the difference. We are going to give a much higher score to the values of much. Then in this case, the median, it's still the same. It's number 2, it's sum. But the means are different. The mean in this case is 1.78, which would correspond to somewhere between little and sum, somewhere between those two. But in this other case, the mean would be 2.44, which would correspond to somewhere between sum and much according to this scale. So what we see here is that the nature of the variable is ordinal. None comes before little, before sum, before much. And therefore the median makes sense. Regardless of what numerical assignments, if we were to assign numbers, the median is still the same, but the mean is not. So there has to be a very, very, very good reason for why we choose this value of 5 instead of 3. Just because of that change, the median remains the same, but the mean does not. So we might be biased in our results just because of this assignment. And let me also show you the example of interval versus ratio. And we're going to talk about temperature here. On the one hand, we have the physical temperature, the physical quantity we are interested in, or the physical property, the temperature of a certain body. And we could measure that in different scales. Most typical Kelvin, Celsius, and Fahrenheit. Now, the point is, if we use Kelvin, we are in a ratio scale. If we use Celsius and Fahrenheit, we are on an interval scale. Even if we are measuring exactly the same physical quantity, depending on the scale we use, we are going to be allowed to do one thing or another. Why is this important? Because we have this notion of absolute zero, which corresponds to, by definition, 0 degrees Kelvin. If we transform the data, over here we have how to convert from one to the other. If we were to compute this in Celsius, that corresponds to negative 273 Celsius. Or in Fahrenheit, negative 460 Celsius. Let's compare at different points of the scale to see what happens. So 300 Kelvin corresponds to almost 27 Celsius and 80 Fahrenheit. 600, which is twice as much, corresponds to 326 Celsius, 620 Fahrenheit. 1200, which is 4 times as much as 300, corresponds to 927 Celsius and 1700 Fahrenheit. The important point here is that if we look at the distance between those points in the scale, at the magnitude of the differences, then yes, in Kelvin we have plus 300 when we go from 300 to 600, and plus 900 when we go to 1200. Those are exactly the same as we would have in the Celsius scale when going from here to there and from here to there. And likewise here with the Fahrenheit, it's just a different number, but the proportions are the same, 540, and then 3 times as much here with 1620. So we are meeting the conditions for an interval scale. But what about ratios? Well, we know that 600 is twice as much as 300, and 1200 is 4 times as much. But if we go to the Celsius scale or the Fahrenheit scale, we see that those ratios do not work anymore. 772 and 2117. So temperature is a case in which even if we are to measure exactly the same physical property, the temperature of a body, then depending on which scale we use, we are going to be allowed to do certain operations or not. So if we use kelvins, we are allowed to multiply and divide values. We are allowed to compute things like coefficient of variation. But if we use Celsius or Fahrenheit, we are not. And this is why if we look at scientific work that has something to do with temperatures, they typically perform all the operations in the Kelvin scale. But then when they have to report numbers, they usually use the Celsius or the Fahrenheit scale. Why? Because it's easier for us humans to get a notion or a sense of how big the numbers are. We all know more or less what 27 degrees Celsius feels like or 80 degrees Fahrenheit, but we have no idea what 300 Kelvin feel like because we're not used to kelvins, even if they are exactly the same temperature. And we see that Celsius are preferred to report all these numbers because then the relative difference between any two numbers is the same in Celsius and Kelvin, like the plus 300 or plus 900 degrees we had here in this example.